You know, every single time you click a link, literally billions of invisible digital envelopes are firing across the globe in a matter of milliseconds. Welcome to this explainer. Today, we're diving into a foundational piece of tech that absolutely rules our modern lives, even though most of us barely give it a second thought. I'm super excited to guide you through this because we're going to break down exactly how the data you're consuming right now found its way out of billions of devices and landed perfectly on your screen. It's all about demystifying IP addresses, which are, quite literally, the Internet's postal service.
We've got a quick roadmap to guide us today. We'll cover the Internet's postal service, the big shift from IPv4 to IPv6, public versus private addresses, the absolute magic of NAT, and finally, wrap up with static versus dynamic IPs. Let's just jump right in. All right, Section 1, the Internet's postal service, and how data actually finds you. Let's start with the fundamental reason why these addresses even exist. Think about it like this. Just like a friend needs your physical home address, the zip code, street name, house number, for a postman to deliver a physical letter, computers need a digital address to send you, say, a downloaded file. It's super easy to picture physical mail delivery, right? But the digital world relies on a massive, hidden physical infrastructure too. Without an exact numeric sequence identifying your destination, your data simply has nowhere to go. All those underground cables, the massive underwater fiber optics, the global wireless signals, they all completely rely on knowing your exact, precise location.
So what is it exactly? Well, an IP, or Internet Protocol address, is simply a unique numerical label assigned to your specific device. It's built on a really strict set of rules, that's the protocol part, that basically makes the entire interconnected web function. It identifies your host interface and pinpoints your exact network location. It is, for all intents and purposes, your device's ultimate online identifier. Can you even imagine a world without IP addresses? Cloud storage? Gone. Instant streaming? Wouldn't work. We'd literally be dragged right back to the dark ages. We're talking buying physical CDs just for storage, scouring actual newspapers to find job listings, and standing in those endless, miserable lines just to buy a train ticket. The IP address is absolutely the unsung hero that makes all of our digital convenience possible. Moving on to Section 2, IPv4 versus IPv6, and the great address shortage. Let's zoom in on the actual numbers here and talk about why the entire internet recently had to undergo a massive global upgrade.
So for a long time, we relied on a system called IPv4, which was a 32-bit address system. Because it uses a sequence of 32 ones and zeros, the absolute maximum number of unique devices it can handle is roughly 4.3 billion. Now, 4.3 billion sounds like a massive number, doesn't it? But we burned through that limit shockingly fast as digital devices totally took over the globe. Turns out, when your TV, your watch, and suddenly even your smart refrigerator need their own internet connection, 4.3 billion addresses get eaten up pretty fast.
To solve this massive shortage, engineers invented IPv6. And the contrast is pretty wild. IPv4 uses a 32-bit decimal format, broken into 4 segments called octets, with each one holding a number from 0 to 255. IPv6, on the other hand, massively expands this to 128-bit hexadecimal format. It breaks the address down into 8 groups called hextets, separated by colons. The absolutely crucial takeaway here is that IPv6 is an upgraded 128-bit alphanumeric protocol. And because it uses 128 bits, it gives us an exponential 2 to the power of 128 addresses. That is a number called 340 undecillion. To put that massive number into perspective, that's enough IP addresses to assign one to every single atom on the surface of the Earth and still have plenty left over. It completely and utterly eliminates the address shortage for countless generations, all while bringing in some really nice built-in enhancements for routing efficiency and security. To really grasp the sheer scale of this IPv6 upgrade, let's just look at one tiny piece of it. Remember those hextets we just mentioned? Just one of those 16-bit IPv6 hextets can range from 0000 all the way up to FFFF. And FFFF in hexadecimal translates to exactly 65,535 in decimal. That means there are over 65,000 combinations packed into just one of the 8 segments of a single address. The scale is just mind-boggling.
All right, Section 3, public and private addresses, and your local setup. Let's zoom back out from the intense math for a second and look at how this applies directly to your phone or computer right now.
There are actually 2 different types of addresses your home network deals with every day.
If you were to check your device right now, your IP address likely starts with 192.168. This is your private IP address. It's used strictly inside your local home network, and it is totally non-routable on the public internet. But to actually talk to the outside world, you need a public IP address. This is a unique, globally routable address that is assigned to you by your internet service provider.
If you want to see exactly what public face your home network is presenting to the entire globe right this second, it's actually incredibly easy to find out. Just open up your browser and type "What is my IP?" into Google. Google will instantly spit back the exact public address that your internet service provider has assigned to your current connection.
Which brings us to Section 4, the magic of NAT and bridging the gap. Understanding that we have both public and private addresses brings up a really fascinating contradiction.
It kind of begs the question, right? How in the world can a single device have two totally different IP addresses at the exact same time? Think about it. If your smartphone has a private address of 192.168 on your local router, but uses a public address for the broader web, how do those two different identities actually talk to each other without losing the data somewhere in the ether? The answer is this brilliant piece of technology called NAT, or Network Address Translation. You can kind of think of NAT like the mailroom of a giant corporate office building. All the internal employees have private office numbers, but to the outside world, the whole building just uses one public street address. NAT is basically the mail clerk sorting it all out. It seamlessly modifies and translates your private IP address into your public one whenever you need to access external websites.
Here is the exact journey your data takes. Step 1, your data leaves your phone using its private IP. Step 2, it hits your router, where NAT steps in, modifies the outgoing data packet, and translates it to your public IP. Step 3, the data traverses the massive public internet to reach its destination, like a YouTube server. And finally, Step 4, when the video data comes back, NAT translates that public IP response back to your specific private device almost instantaneously. This doesn't just allow multiple devices in your house to share one public IP, which, conserves addresses, but by masking your internal devices, it actually adds a super crucial layer of security. It makes it way harder for external entities to directly access your phone or laptop.
And finally, Section 5, Static versus Dynamic IPs, Constant versus Changing. Let's wrap up by exploring how these addresses are actually assigned to your devices and why they might change over time. So, we essentially have two flavors here: dynamic IPs and static IPs. Most of us at home are using dynamic IPs. These are constantly rotating addresses assigned completely automatically by a network protocol called DHCP. They are incredibly efficient and cost-effective for internet service providers because they can just reuse and reassign addresses from a giant pool whenever you connect. On the flip side, we have static IPs. These are fixed, permanent addresses manually assigned by a networked admin. They literally never change, which makes them absolutely vital for hosting DNS servers, websites, or any services where a constant, reliable address is required so the public can always find them. Now, because a static IP is a permanent fixture in the digital landscape, it acts like a very distinct, heavy digital footprint. A static IP can actually be traced to reveal highly specific geolocation data. We are talking about pinpointing the exact continent, country, city, and even the specific internet service provider that is supplying the connection to that device.
So, while static IPs offer absolutely fantastic reliability for remote access and hosting, this permanence definitely comes with a trade-off. They are considered much easier to track and therefore somewhat less secure than constantly shifting dynamic IPs. Having a changing address just gives you a bit more anonymity, making dynamic addresses the much more practical and secure choice for our everyday general internet use.
Which leaves us with this final thought. As we rely more and more on these unique numerical labels for absolutely everything we do, from running our smart homes to checking our bank accounts, it's really worth asking yourself, knowing that a static IP can pinpoint your exact city, how much of your daily digital footprint are you unknowingly leaving permanently exposed? Who really has your address? It is definitely something to keep in mind the next time you connect. Thanks so much for joining me for this explainer. I really hope it brought some clarity to the incredible invisible infrastructure running quietly behind your screens.